Hello class, welcome to this lesson on 6.7. We're going to be talking about geometric sequences and series. This is the last lesson in the unit. So we want to be able to represent and use geometric sequences and series. So we want to be able to identify, write, and use them in a given context. So we're going to talk about common ratios, geometric sequences, and geometric series. So this lesson is another use of exponential functions in another application and what are known as geometric sequences. So a sequence is an ordered list of numbers that generally follows some kind of pattern. In Unit 1, we considered a type of sequence known as an arithmetic sequence, which had a common difference between each consecutive term. So for example, 1, 3, 5, 7, 9 is considered a sequence because it's an ordered list of numbers and it generally follows a pattern. Now this is an arithmetic sequence because you have to add or subtract to get to the next number and so on. So the pattern here is you're adding by twos, and that's known as arithmetic. So a geometric sequence is a sequence with a constant ratio between consecutive terms. So for example, if you had 1, 3, 9, 27, and so on, in this case the pattern is that you're multiplying to get to the next number. So if you're multiplying or dividing to get to the next number, that is referred to as a geometric sequence. And the number that it takes to multiply or divide to get to the next number is referred to as the common ratio. And we call that R. So there are two definitions or ways to express a geometric sequence. So the first definition or way of expressing a geometric sequence is with the recursive definition. A recursive definition is a rule that involves repeated application of that rule to previous terms in a sequence. So for example, if we had 1, 3, 9, 27, and so on, well, we just said that in order to get the next term, you got to take the previous term and times it by 3, right? So the recursive definition says take the previous term and multiply by 3. To get 9, I take the previous term and multiply by 3. And that's the pattern, that's the recursive definition. And this can be written, by saying, okay, well, the first term is 1, right? And the next term is going to be the previous term, which we'll call, so if this term is called a n, then this term is called a n minus 1. So we're going to take the previous term and multiply by 3. So the recursive definition is saying take the previous term, multiply it by x amount of number, and this will give you the next term. So it looks something like that. We're going to be talking about that in more detail. And then the last definition is the explicit definition. It's a rule we can use to get one specific term in a sequence. So it's some kind of formula that we use to get a specific term. Alright, so is the sequence shown in the table a geometric sequence? If so, write a recursive definition for the sequence. So they're giving us a list, a list of terms. These are my terms here, 4, 12, 36, 108, and so on. So is there a pattern to this sequence here? And the answer is yes. The pattern is that you're timesing by 3 every single time. So you're multiplying by 3 to get to the next term. So yes, there is a pattern of multiplication, which means that it is a geometric sequence. So yes. In this case, this 3 is referred to as the common ratio. So the common ratio, R, is equal to 3. So we want to write a recursive definition for the sequence. So how do we go about writing that? Well, first we're going to say an equals. So an is used to represent a given term. Okay, so for example, a1 is equal to 4. So this is a1. a2 is equal to 12. So these are the specific terms in that sequence. and then A3 is 36, and so on. Now, to get the recursive definition, well, we know that this is equal to 4 when my n value is 1. So for my first term, I get a number of 4. And then what's the pattern for the next number? Well, I got to take 4 and I got to multiply by 3, right? To get 12. And then I take 12, multiply by another 3 to get 36, and so on. So that's going to be represented with this pattern. So we're going to say that you're going to take, so if this is A2 and this is A1, well, you have to take the previous term A1 multiplied by 3. And if this is A3, you got to take the previous term and multiply it by 3, right? So what we're going to do is we're going to call this AN, and in order to get AN, you have to take the previous term multiplied by 3. So the previous term is AN minus 1, because 3 minus 1 is 2, right? 3 minus 1 is going to give us 2. So therefore, you're going to take A2 and you're going to multiply by 3. So we're going to do this times 3. So we're going to do 3 times the previous term. And 3 times the previous term is going to give us the next number. So this is when n is greater than 1. Okay, so let's see if this definition works. We wrote it down, but we want to make sure that it works. So let's say that I have A4, okay, for instance. I'm going to go ahead and erase all of this now. So let's say we want to find A4. Now we know from this table that this is A4. So we know that that's A4. So in order to get A4, which condition are we going to follow? Well, n is definitely greater than 1, so we're going to be using the bottom case, right? So therefore, we're going to be using the bottom, so we're going to say 3 times A, 4 minus 1. So 4 minus 1 is 3, right? So you're going to take the third term and you're going to multiply by 3. So this is going to be 3 right here. All right, well, what's A3? A3 is 36. So this is A3. So we got to do 3 times 36. And 3 times 36 is 108, which makes sense because that's my A4. So this is a recursive definition, is a certain rule that tells you in order to get one term, you got to do something to the previous term. So that's what the recursive definition comes into play, is that you're repeating some kind of pattern to the previous number. Okay, so that's the recursive definition right here. So what is the general form for the recursive definition? It's as follows. So basically, the recursive definition can be expressed as a piecewise function, and it looks like this. So you take this is your first term in the sequence. In our example earlier, it was 4. And then for the second entry, you're going to take the common ratio. Remember, this is the common ratio. And you're going to multiply by an minus 1. You're literally just going to write an minus 1. Okay, so remember, for our previous example, we said that an was equal to 4 when n was 1, and it was equal to 3 times an minus 1 when n is greater than 1. So this is from the previous example. That's how it looks like. All right, so let's look at another example. Is the sequence given below a geometric sequence? If so, write the recursive definition for that sequence. So we're going to see if there's a pattern in the numbers here. So if we look at the numbers, first off, you can kind of tell, well, what we're going to do is we're going to see, well, is there a number that if we multiply or divide, we get to the next term? So how do we go about doing that? Well, what we're going to do is we're going to take the, let's do this one right here, the first question mark. We're going to take the 9.6 and divide it by 12, okay? So, and that'll give us, hopefully, our common ratio. So let's take 9.6 and then divide it by 12. Okay, and then we'll see if that number is the same throughout. Okay, so if you take 9.6 divided by 12, that's going to be 0.8. Now let's go ahead and, so we know that this here, we have to take 12 and we got to multiply it by 0.8 in order to get 9.6. Okay, so that's what we got to do to 12 to get to 9.6. And then for the next set, for the next question mark now, we're going to take 7.68 and we're going to divide it by 9.6. And if you did that, that would also be 0.8. Okay, so this actually holds true as well, right? So we got 0.8 here. And just in case, we'll do it one more time. 6.144 divided by 7.68. And that is also equal to 0.8. So therefore, this right here is a geometric sequence. So because you have to multiply or divide by the same number to get the next number. So yes, and the common ratio in this case is 0.8. Now, if so, write the recursive definition. So remember, the recursive definition was an equals a1 when n equals 1, and r times an minus 1 when n is greater than 1. So if we use that definition, if we apply that definition, well then my an is equal to, well, what's my a1? This is my first term, remember? So this in this case is 12. So this is 12. So we got 12 when n equals 1. And what's my r? Well, we found my r is 0.8. So we have 0.8 times an minus 1 when n is greater than 1. And that's my recursive definition. Pretty simple. So this means that you start out at 12, and then to get any of the other terms, you're going to take 0.8, multiply by the previous term, and that will give you the next term. All right, so we talked about the recursive definition. Now what we're going to do is we're going to talk about the explicit definition. We're going to actually convert the recursive to the explicit definition and reverse that as well. So we're going to convert explicit to recursive. So for the first part, given the recursive definition, what is the explicit definition for the geometric sequence? Okay, so first off, remember that the recursive definition was a1 when n equals 1 and r an minus 1 when n is greater than 1. So if you compare these two forms, you can clearly see that r is equal to 1/2. All right, you can also clearly see that a1 is equal to 5. Okay, so a1 is 5. Okay, so what this is saying is that you're going to start at 5, right? So the first term is clearly going to be 5. Let's go ahead and write out the what the sequence looks like. And then you're going to take the previous term, you're going to take to get this number, you're going to take the previous term, which is 5, and multiply by 1/2. So we're going to times that by 1/2. All right, so if we times 5 by 1/2, we're going to get 5/2. 5 times 1/2 is 5/2. To get the next term, you're going to take now the previous term, multiply by another 1/2, which is 5/4. And then you're going to keep going. So then you're going to times that by 1/2. So now you get 5/8, and so on. All right, so basically what we did is we kept taking 5, multiplying it by 1/2, 1/2, 1/2, right? So what we did here, I'm going to write this in another way. We're going to write this as 5, and then we did 1/2, we multiplied that by 1/2. For the next one, for this 5/4, we did 1/2 times 1/2, right? Which is 1/2 squared. What's 1/2 times 1/2? Well, 1/2 times 1/2 is 1/4. And then 5 times 1/4 is 5/4. And then we multiply by 1/2 yet again, and we get cubed. So we're basically multiplying by 1/2 a bunch of times, and those halves are building up over time. And that's how we get, the 5/8, the 5/4, and so on. So the explicit definition is given by the following formula, right? So in this case, we can kind of tell, the explicit definition. So it's an equals So clearly we start out with 5, right? So 5, and then we got a half, right? So we got a half. This is clearly a pattern, 3, 2, 1. And then what's the pattern for this first 5, you may ask? Well, technically, there is a half there, but it's raised to the 0. So I'm going to go ahead and include that here. We have a half there technically, but it's raised to the 0. And we know that anything to the 0 power is 1. So this is 5 to the 1 power, 5 times 1, I mean. So basically it's 5 times 1/2 raised to the n minus 1 power. All right, so this we know that this is a1. And we know that 1 minus 1 is 0. And then we know that this here is a2. And we know that 2 minus 1 is 1. And therefore, that's how we get this exponent right there, n minus 1. So we take the term number, subtract 1. All right, so this right here is my explicit form. I can get any terms in the sequence by using this format here. So basically, the explicit definition for a geometric sequence, we'll go ahead and write it out here, is given by a sub n equals a sub 1 times r to the n minus 1 power. So this is my definition for explicit for geometric sequences. This is for geometric sequences. All right, so we went over what the recursive definition is for the geometric sequence. Now this is the explicit definition. So I can get any term from the sequence using this definition. All right, so now given the explicit definition, which we just were able to find, let's see here. Given this explicit definition, what is the recursive definition for the geometric sequence? So this time they're giving us an explicit definition. We want to convert it to the recursive definition. So how do we go about doing that? Well, first off, from the explicit definition, remember we said that the explicit definition is an equals a1 times r to the n minus 1 power. So now we know what the explicit definition looks like. So we can go ahead and compare stuff. So we know that 3 is equal to a1. Clearly, we can see that from the form. And then we have r. We have the n minus 1, of course. And then we can tell that r is equal to 2. So we have a1 is 3, and r is 2. All right, so basically what this is saying is that we're multiplying, we start out at 3 and we multiply by 2 to get to the next term, and so on. And we keep repeating that pattern. So like the first term in the sequence is 3. And then the common ratio r says to multiply that by 2, and that'll give you 6. And then multiply by another 2, and that'll give you 12. Multiply that by yet another 2, and you get 24, and so on. There's the pattern. So the recursive definition is an equals, you're going to take your first term. My first term is 3. So my n equals 1 term, that's 3. Anything else other than 1, like the second, third term, and so on, you're going to take the common ratio r, and you're going to multiply by the previous term, which we call an minus 1. And that is my recursive definition. Again, if we want to check this definition, we know that this is a1, we know that this is a2, we know that this is a3. So if I wanted to find, say, a2, well, I'm looking at this rule right here, right, for a2, because 2 is greater than 1. So we're going to take 2 multiplied by a, and then n in this case is 2, because that's my n, so 2 minus 1. Well, 2 minus 1 is 1, so we got 2 times a1. Well, what's a1? Well, a1 is 3. So we're going to do 2 times 3, and that'll give us 6, which, of course, that's what we got here. So this is how we use the recursive definition. All right, so I got another example. We're going to actually be using a geometric sequence to model the following scenario. So we know that a geometric sequence can be used, in this case, to describe the growth of bacteria in an experiment. On the first day of the experiment, there were 9 bacteria in a petri dish. On the 10th day, there are 3 to the 20th bacteria in the dish. How many bacteria were in the dish on the 7th day of the experiment? All right, so they're talking about a geometric sequence here. So therefore, we want to use some kind of sequence formula, right? So let's use the explicit definition. The explicit definition, if you recall, is an equals a1 times r to the n minus 1 power. So that's my explicit definition now. So now my first day, so we're going to say n is the number of days here, right? N is the number of days. So on day 1, we have 9 bacteria. So this means that this is A1. A1 is equal to 9 bacteria. Now it says on the 10th day, there are 3 to the 20th bacteria in the dish. So this means that A10 is equal to 3 to the 20th power. So we got our A1, we got our A10. So we want to figure out, okay, what's the amount of bacteria in between these days, right? What happened on day 7? We're interested in what happens on day 7. So A7 is a big question mark for now. So using this formula, let's go ahead and plug in what we know, right? So we know that A1 is 9, so let's plug that in. Let's plug that into our equation here. And then we know that A10, so we know that when n is equal to 10, that's when n is 10, that the value is 3 to the 20th. So we're going to plug this in for an, and we're going to plug in this for a1. And then for n, well, we know that n is 10, right? So we're going to plug that in for 10 there. Okay, so let's go ahead and plug those numbers in. So we have 3 to the 20th equals 9 r to the 10 minus 1. All right, so we used the information they gave us. We're going to go ahead and simplify this now. So we got 3 to the 20th equals 9 r to the 9th power. Our goal is to figure out what r is, because we don't know what the common ratio is. What is this pattern that we're multiplying by to get to the next term, right? So we need to figure that out. And we can't figure it out right now until we solve it. So we're going to go ahead and divide by 9 on both sides. So now we have 3 to the 20th over 9 equals r to the 9th power. So our goal is to solve for r here. The only way to get rid of the 9th power is to do the 9th root of both sides. So we're going to go ahead and do the 9th root of both sides. And now these cancel with the radical. So now we have r is the 9th root of 3 to the 20th over 9. Now, of course, we're going to go ahead and get what that number is. So we have 3 to the 20th So when you do the 9th root of that, you get exactly 9. All right, so now we know that the pattern is 9. All right, so we got our common ratio R. Now we're going to figure out how many bacteria we have on day 7. So let's go ahead and use the formula again. We're going to be using the same formula that we used earlier, the explicit term. But now we know that we're trying to find A7. So we're going to say this is A7 now, trying to figure out what that is. So now we know that n is equal to 7 because we're trying to figure out for day 7. and we got A1. A1 stays the same. A1 is still going to be 9 bacteria. Now we got our new R of 9. So I'm just going to plug that in. And N is 7, so we're going to do 7 minus 1. All right, so now A7 is equal to 9 times 9 to the 6th power, which is the same thing as 9 to the 7th power. And we got 4 million. So we're going to get 9 to the 7th, but I'm going to go ahead and get that number out as well. I'm just curious to see what that number is. 4,782,969 bacteria. It's a lot of bacteria on day 7. All right, so a geometric sequence is the sum of the terms of a geometric sequence. So a geometric series as opposed to a geometric sequence. So remember that a geometric sequence is an ordered list of numbers which has a common ratio that you multiply or divide to get to the next number. The series is when you add the terms in the geometric sequence. A partial sum is the sum of a certain amount of terms of a sequence, so like a small amount. So for example, let's say we're looking at this sequence. Now this is a geometric sequence because we're timesing by 3 to get to the next number, and so on. So we know that this is geometric. The first partial sum is going to be the first term, which is just going to be 1. The second partial sum is going to be given by taking the sum of the first two terms, 1 plus 3, and then you expand that to the third partial sum and add the first 3, and so on. So the fourth partial sum, well, in that case, would be adding these 4. So to convert this sequence to a series, you're simply gonna add up all the terms in the sequence. So therefore, you just add up all the terms here, and that now becomes a series. All right, so very easy to distinguish between sequence and series. Now the general equation of a series is given by this following formula. So this is going to be a formula we're going to be using for series. So this formula tells you no matter how many terms you add, it'll tell you what you get when you add up the terms in that sequence. So if you want to add the first 5 terms in that sequence, this formula will do that for you. If you want to add the first 343 terms in the sequence, this formula will also do that for you. So recall that another way to express a series is with sigma notation. So far, we said that we can express a series by simply adding the terms in the sequence, right? This should be a 9 and 27, just like in the previous example. Now we can take this and we can convert it to sigma notation. So how does that look like? Well, it's called sigma notation because we got the Greek letter capital sigma there. And remember that sigma means that you're going to be doing the sum. So sigma here equals sum. And sum means you're adding. Okay, that's why it's called a series, because series you're adding stuff together. All right, so that's what the sigma stands for. This is called the lower limit, and this tells you the number that you're going to start out with. So you're going to start out with the first term, and then this is your upper limit, and this is telling you where you're going to end. So your lower limit is your beginning point, your upper limit is your ending point. So if you want to express the series, and if you want to use sigma notation, well, let's say we have this as an example where you're going to start with plugging in 1 into n, and in that case you get 1 minus 1. Next, you already plugged in 1, so now you're going to go ahead and plug in n equals 2. So this is when n equals 1. Now we plug in n equals 2, then we plug in n equals 3, and so on. When do we stop? We stop until we get to the upper limit. And then once we plug those numbers into the formula, right, this formula right here, then we add those together. The sigma means, remember, the sigma means sum. So the sigma means to add. So this is why we're adding all the terms in that sequence. So now this becomes a series. So that's what sigma notation means. Take that formula, apply it multiple times, and then add them together. All right, so if we did this, we're going to get 3 plus 3 over 2 plus 3 over 4 plus 3 over 8 plus 3 over 16. Again, we call this the sigma form, and the right side we call the expanded form. Okay, so the expanded form is, like the example that we did earlier with the 1 plus 3 plus 9 plus 27. We call that the expanded form. And then we can convert that to the sigma form and vice versa. We can go backwards between the two forms. All right, so then the sigma notation, expanded form, and formula for the geometric sequence, we're going to go ahead and summarize those three things now for the geometric sequence. So we got the sigma notation form, which is this right here. So that's how the sigma notation form looks like for a geometric series. Now, the expanded form looks like that. So we got our sigma notation form, so this is our sigma form. We got our expanded form. How did we get the expanded form? It's pretty simple. All you got to do is you're going to plug in 1 into there, right? And 1 minus 1 is 0. So we get r to the 0. Well, we know r to the 0 is just 1, so that goes away, and we're left with a1. So that's how you get the first one. Next, you're going to plug in m equals 2. So now we get r to the 2 minus 1. Well, 2 minus 1 is 1. So we get r to the 1 power, which is this guy right here. All right, and then if you plug in 3, you're going to get squared. So this is when m equals 3. This is when m equals 4, because we take away 1, and so on. So that's how we get the expanded form from the sigma form. And then the formula for the geometric series, we're going to go ahead and recap that, is given here. So this is the formula for the geometric series. So this is all the forms thrown at you, at the same time. So that way we can kind of compare the three forms. Now this formula, it can be expressed either this way, or if you want to figure out what it is when you add them, you use the formula. Okay, so we're going to do an example. Write the expanded form of the given geometric series and find the sum of the series. So we're given the sigma form. We want to figure out what the expanded form is, and then we want to use the formula to find the actual sum. So we're doing the right two things in the previous slide. Okay, so we got the sigma. So what does this sigma mean? Well, first off, we're going to take the n equals 1. We're going to plug that in. That's given right here. So this is n equals 1. Then we plug in n equals 2. Then we plug in n equals 3, all the way up to n equals 7. All right, so we're going to plug in from 1 to 7. And then we sigma those terms. We add them. So we're adding them together. All right, so now that we get that, we're going to simplify this. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. 3, and so on. Next step, anything to the 0 power is 1. 2/3 to the 1 power is 2/3. 2/3 to the second power, well, 2 squared is 4. 3 squared is 9, so that's how we get 4 over 9. Now, 2 to the third, 2 to the third is 8. 3 to the third is 27. And that's how you get all the terms. All right, next we're going to go ahead and multiply those terms together. 3 times 1 is 3. 3 times 2/3 is 6/3. Remember, this is 3 over 1, and then 3 times 1 is 6. 1 times 3 is 3. This is 3 over 1. 3 times 4 is 12. 1 times 9 is 9. And so on. Repeat that pattern, and we get those numbers. And then lastly, we know that 6 divided by 3 is 2. 12 divided by 9 is 4/3. 24 divided by 27 is 8 over 9. So we went ahead and reduced everything. So we had to divide this by 3 to reduce it. We had to divide this by 3 to reduce it as well, and so on. We just went ahead and reduced everything. All right, so this right here is my expanded form. Okay, I simplified it, but that's the expanded form. Okay, so we know our expanded form. That's what it is. Now we need to figure out, well, what is this when I add them all together? Okay, so of course I can just literally add them all together and get my sum, right? And that would be perfectly fine. However, suppose that this 7 were a 105. Well, you're not going to be adding 105 terms, right? So what we're going to be doing is we're going to be showing you the formula way of doing this, okay? So to find the sum, we're going to be using the sum formula. Recall that we mentioned this earlier. So what is A1 in this example? Well, A1 is 3, because remember that that's the first term. The first term is A1. And the R is 2/3 because we're multiplying by 2/3 to get to the next number. That's what we did earlier. We multiplied by 2/3. And that's your R. All right, so we got A1, we got R. What's N? N is 7. That's the last term that you're interested in. So what we're going to do is plug those into that formula. We know that N is 7. We know that A1 is 3. And then we also know that R is 2/3. So we went ahead and plugged it in. All right, so now that we plugged it in, we got to do the math. So we got 2 to the 7th power is 128. 3 to the 7th power is 2187. 1 minus 2/3 is 1/3. All right, we got to do 3 times. So we went ahead and did this. We needed a common denominator. So the common denominator is 2187. So I'm going to convert this 1 over 1 to 2000. We got to multiply by 2187 over 2187. And then we subtract those two. And that gives us this. And then we got to do 3 times that. So 3 over 1 times that. So 3 times that. And then 1 times that. So that's what we get when we do that. So 3 times 2000 is 6000. 1 times 2000 is a 2000 number. And then remember the keep, flip, change, right? Keep, change, flip. So you keep that, you flip that. All right, and then that changes to multiplication. So then we multiply straight across, and we get that fraction. This times that is that. This times that is that. And then we went ahead and reduced that by dividing by, whatever they have in common. So this right here is my sum. So using that formula, we're able to get the sum. Of course, you're able to get this as a decimal. If you got this as a decimal, that is perfectly fine. I just went ahead and used the fraction form. All right, guys, thank you for watching the video. I hope you took 1 or 2 things from this, and I'll see you in the next one.